All right. Hi, everyone. Thank you for your time today. I'm Santosh Bhavani, and I'm a senior product manager in Amazon SageMaker, and I'm really excited to introduce Inference Recommender to you today. So before we jump in, I just wanted to start with a brief overview of SageMaker for anyone that's new to the service. Amazon SageMaker is the most complete end-to-end ML service. We built SageMaker from the ground up to help every developer and data scientist build, train, and deploy ML models faster and at a lower cost. To accomplish this, we provide the tools for every step of the ML development lifecycle in one integrated, fully managed service. And in fact, we launched 50 plus capabilities in the past year alone, all aimed at making this process easier for our customers. Now, SageMaker offers some key benefits when it comes to hosting ML models. With SageMaker, you can set up an endpoint in minutes and to get predictions from your models. Infrastructure setup, patching, and updates are taken care of automatically. And there are built-in metrics and logging emitted to Amazon CloudWatch so you can monitor all your ML deployments. In terms of performance, SageMaker provides high availability with support for deploying tens of thousands of models on a single endpoint. We have over 70 different instance types for you to choose from, and all of them have configurable auto-scaling policies to meet your workloads. Finally, MLOps features of SageMaker, such as SageMaker pipelines and project, can help you deploy models repeatably and at scale. You can also version and manage your models using Amazon SageMaker. And as you start using your models in production, Model Monitor can alert you on any data drift or model performance issues. While SageMaker provides a lot of useful tooling and services around ML inference, there's a larger set of decisions data scientists have to make in order to get a performant deployment. And I'd like to walk you through some of those decisions by taking a look at the layers below when you host a model on SageMaker. First, ML projects start with your choice of framework. The most popular ML frameworks are TensorFlow, PyTorch, MXNet. But SageMaker actually provides managed containers and SDK support for all major ML frameworks. As new algorithms and frameworks are constantly being developed, we continue to expand our support. For example, we recently added support for Hugging Face. Hugging Face is a leader in natural language processing, and if you're a developer working in NLP, you can rely on SageMaker to provide containers and SDK support to build on top of Hugging Face. The next layer down is your choice of model server. So the role of a model server when you're deploying an ML model is to take inference requests and efficiently route them to one or more ML models. There are some model servers that are optimized for your framework, such as TensorFlow Serving, and others like NVIDIA Triton, which are framework agnostic and come with additional hardware level optimizations like GPU optimizations. Whatever model server that fits your framework or use case, AWS Deep Learning Containers is a really easy way for you to swap out different model servers for your use case and identify which ones are most performant for your use case. And finally, at the bottom layer are your compute instances and software accelerators. AWS provides the broadest and deepest portfolio of ML compute instances. We have CPU and GPU instances of varying memory and cores, and we also have Inf1 instances, which are powered by AWS Inferentia. It's a homegrown chip that provides high performance at a low cost. Similarly, we released Graviton, which is another homegrown chip based on ARM and provides high performance and very low cost as compared to x86-based instances. As for software accelerators, many of the accelerators you find, such as NVIDIA TensorRT, Intel 1DNN, are hardware specific. With SageMaker Neo, it's a SageMaker service that helps you automatically optimize your model regardless of your instance type and underlying hardware. It uses model compilation along with hardware-specific kernel libraries to accelerate your inference. Now, I covered a lot of different parts of the stack here, and the problem with all this choice in your inference stack is that optimizing inference becomes a nonlinear task, and there's a lot of experimentation involved to get the performance and cost that you need. So when you're getting ready to deploy your model, you might first start by selecting an instance type out of the 70 plus available instances. Then you might go ahead and optimize your model for different hardware using software accelerators, kernel libraries, model level optimizations such as quantization, compilation. And then next you'd have to then select your model server, set your parameters such as the number of threads or workers, set your instance count and auto scaling policies. And finally, you have to conduct extensive load tests to validate that all the choices you made previously meet your latency and throughput requirements and that the costs are acceptable. So the problem with this approach is that there are many open source tools for load testing, but it requires setting up your own test suite, managing configuration files, and if anything changes, this whole process has to be repeated again. It has to be repeated for every single ML deployment. So what we're introducing today, SageMaker Inference Recommender, eliminates this complexity, and I'm really excited to introduce that this is the first performance testing service for machine learning. Inference Recommender makes it easy for you to automate your load tests and optimize model performance to select an endpoint that delivers the best performance at the lowest cost. Now, let's see how SageMaker Inference Recommender makes it easy for MLOps engineers and data scientists to reduce time to get your models into production. Inference Recommender enables you to first get started in minutes with an instance recommendation that suits your unique ML workload. It allows you to conduct custom load tests across instance types and review them all within a single panel. And finally, it provides you an optimized endpoint configuration. This goes beyond instance type and provides you an instance count, tuned container model server parameters, as well as perform model level optimizations. Now, you can get started with Inference Recommender with just 3 things. You need your ECR, your container image location for your inference container. You need your S3 locations for your model artifacts and sample payloads to send to your model. And finally, you need some metadata or information about your model. So for example, if you're working on a task in the domain of computer vision with the task of object detection, and you're building on top of PyTorch as your framework, those are metadata that you'd provide to Inference Recommender. This information will all get stored into model registry, SageMaker model registry, where you can track and version your models as well as integrate with MLOps. From here, once your model is registered, you can then kick off an initial instance recommendation that uses all the model metadata that you provided to identify an optimal set of instance types to conduct a load test. Within 45 minutes, you can expect to get recommendations on instance types, model optimizations, as well as container parameters. Now, if you prefer to select your own instance types and manage your own load tests, you can also do that with Inference Recommender. It lets you input custom traffic pattern, as well as select all the different instance types you want to test for your model and payload. And finally, once your instance recommendations or load test is complete, you can review your performance and cost metrics across all the different endpoint configurations visually from Studio or using your favorite visualization libraries and using the AWS Python SDK or CLI. And once you've selected an endpoint configuration that fits your needs, from Studio, you can now one-click deploy your model to production. Now, let's look at the specific capabilities of Inference Recommender. First of all, to get an instance recommendation, you can use the Python SDK directly and get recommendations directly from your Jupyter Notebook. You can get, Inference Recommenders also integrate model registry, so you have a centralized storage place for all your model artifacts, code, inference container location, model metadata, and any approved instance and content types you want for your real-time inference. And finally, you can review your recommendations, and using Studio, you can go end-to-end and deploy your model in a few clicks. We'll look at the details in our demo, but here's a quick screenshot from Studio showing you different instance recommendations within model registry, and you can see the associated cost per hour metric, as well as useful performance metrics related to latency and throughput, so you can narrow down on what instance type works best for your ML workload. And I mentioned the custom load test capabilities. So if you want to run a custom load test on your own set of instance types, with Inference Recommender, you could customize your load test by providing your production requirements. So what's your throughput and latency for the stopping criteria, and change your traffic pattern, the way you send requests, and choose your instance types to test against. The other task when it comes to tuning performance is when you're choosing parameters for your containers as well as your model server, it can turn into a combinatorial task. There's lots of different variables that you can tune. And the advantage of using Inference Recommender is that when you're running a custom load test, you can sweep through all the different environment variable parameters, such as your number of threads, your workers, or any other parameter specific to your container, and be able to review all those different load tests in a single job and in a single view. So with Inference Recommender, you compare all your load tests and provide you the key performance metrics you need to make your final decision on deploying your model. The other thing I want to point out is our SDKs are easy to integrate with CloudWatch, and we provide sample code. So let's say you want to monitor GPU utilization, or using AWS Inferentia and you want to monitor core utilization. All of that is really easy to integrate along with CloudWatch and Inference Recommender. And here's also another screenshot, so you can see these are all different instance types, and if you had to run these load tests manually, collating those results would take a lot of time. And with Inference Recommender, you can kick off multiple parallel load tests at once. And to dive deeper into what the recommendations actually include, so Inference Recommender, in addition to your instance type, it provides you an initial instance count. So if you're setting up a request-based auto-scaling policy, you'd want an initial instance count that meets your throughput and latency constraints. And that's exactly what Instance Recommender provides from its recommendations. It also recommends model-level optimizations powered by SageMaker Neo. So if you provide your model in the required parameters for SageMaker Neo, it'll automatically compile your model across different instance types. And finally, it provides container parameter settings. So if you're using an AWS deep learning container to select your model server, so for example, if you're using TensorFlow serving, OMP num threads is a common variable that you might want to tune. And with Inference Recommender, you can get an automatic tuned parameter for that variable. And finally, the integration with Studio makes it very easy for you to visually compare all your different options. So here's a quick screenshot from Studio where you can see all the different endpoint configurations from a custom load test, as well as the associated cost and performance metrics, and some useful filters to help you sort by cost, latency, throughput. Now, let's take a look at some real-world examples of customers that have used Inference Recommender. Loka is a full-stack consultancy accelerating AI/ML for AWS customers. Their engineers used to spend a huge amount of time and energy setting up cost-effective performant deployments for their end customers. And with Inference Recommender, they're now able to deploy to production in minutes using the recommended instance types from Inference Recommender. Another one I wanted to highlight is Holma, a Singapore-based health tech company that launched FoodDX, an app to help people improve their diet and health. Their ML scientists used to handle both the model building as well as the DevOps and MLOps activities. So they used to spend a large portion of their time load testing to make sure that their algorithms meet the latency requirements for the end users looking for diet recommendations. With Inference Recommender, they can now go back to focusing on algorithm development and spend less time on the MLOps and DevOps tasks. And finally, I want to highlight the really important work of Echo, a cardiopulmonary digital health company. Echo's FDA-cleared platform provides real-time disease detection where every second matters. With the ML model-level optimizations suggested by Inference Recommender, Echo was able to speed up their model predictions, which ultimately improves turnaround time for their patients. Now let's switch over and look at a quick demo. Okay, there we go. So here's a sample notebook. If it's not already published, it should be published by end of day into the SageMaker examples. But I just want to walk you through the different steps in the code of what it takes to get started with Inference Recommender. So in this example, we're looking at a TensorFlow image classification model. It's a basic Resident 50 model, but of course, Inference Recommender supports all frameworks that SageMaker supports. In reality, any container that you want to test should be supported by Inference Recommender. So for the setup steps, we're using a notebook instance here. So I'm going to go ahead and select the Conda TensorFlow P36 kernel. This uses TensorFlow 1.15.5 and Python 3.6. And here we're just importing some basic methods from SageMaker and storing some useful variables like the region name, a SageMaker client, and then a session that we can a SageMaker session we can reuse for different tasks. The next step is providing your machine learning model details. So here you can provide as much information as you feel comfortable with, but you can imagine it's a recommendation engine powering Inference Recommender. So the more information you provide about your ML framework, the domain you're working on, whether it's computer vision, natural language processing, or the task, Inference Recommender uses this information to identify the best set of instance types to test your model against. So here we're just providing the basic information of TensorFlow, the TensorFlow version, the model name, model domain here is computer vision, and the task is image classification. And using this, the next part, the next input we need is the model archive itself. So the way SageMaker refers to model archives is really your exported model. In this case, we're using TensorFlow, so the format is a TensorFlow saved model. And it's packaged in a tar gzip, so just a regular tarball. And here we're including both the pre-trained model as well as the code into two separate folders. And with here we're just taking a model using TensorFlow Keras applications and outputting it, exporting as a TensorFlow saved model. And once we create a tarball with both the model and inference code, the next step is to upload to S3. This is where the SageMaker session variable comes in handy. Using the SageMaker SDK, we can quickly upload the data to S3, set a folder, and then we have our path here. Once you have your model and inference code in S3, the next step is to prepare your sample payload archive. So for any load test, in order to have results that represent what you'd expect in production, you want to send the most similar data to what you'd expect to have in production. So here we're taking a set of images, putting it into an archive, and Inference Recommender will automatically sample from this archive. So it's recommended that you have a variety of samples that represents the distribution of payloads that you expect in production. So once we create a quick tarball of all the payloads, in this case it's just various JPEG images, we upload that to S3 again using the SageMaker session variable. And finally, we come to the part of putting all this information into model registry. So if you're new to model registry, just as a quick primer, model registry is it's a hierarchical system where you have a model group which can hold multiple versions of your model. So if you're training multiple versions of the same model or testing multiple different variations of the same model, model registry is a good data store for that, as well as an easy way to connect to your MLOps. So if you want to train a model and then automatically deploy it, model registry makes that automation a lot easier. And here we're using model registry as a way to store all this metadata about your model. So we have your container image URL, your model metadata, and your model inference code and artifacts. So one step I missed earlier is your actual inference container image. I'd recommend everyone to check out the open source AWS deep learning containers. These are supported for all major ML frameworks, comes with a model server, and it's optimized for that framework. So it's a very easy way to get started deploying your ML models. So here we're just going to use the CAN TensorFlow inference CPU model container image. Next, we create a model group, and all that involves is providing a model group name and a description. And finally, once we have an empty model group, we can register our model version or model package. So the model package holds all the information. It has our domain, which in this case, computer vision, our task, which is image classification, the sample payload, URL and S3, and then has a description and a few other fields. This is also a key aspect of Inference Recommender I want to point out, that it can help you perform automated ML model optimizations. So if you're not familiar with SageMaker Neo, it's a service that can take your ML model and perform optimizations that improve your performance without affecting your accuracy. So the only input needed for SageMaker Neo is this field called data input configuration. It requires your input layer name and the shape of your input layer. I provided all this code, but basically there's a very useful CLI tool from TensorFlow called Save Model CLI that you can point at your model directory, and it'll give you the shape of your model. So we can see here that the shape is 224 by 224 by 3. -1 is just a placeholder for the batch size. And the name of the input layer is input_1. So using this information, we set up this field. And using this, what Inference Recommender does is if you're testing your model against inferentia, which requires compilation, or if you want to optimize your model on CPU or GPU, by providing that extra information, it automatically runs those model optimizations in the background for you. And this works across PyTorch, MXNet, XGBoost, and many other model types, and many other frameworks. Here we're going to set a few other parameters. The input MIME type here is a required parameter just to let the endpoint know what the content type looks like for your payload. And I'm also setting the supported real-time instance types. So let's say there's only a certain set of instances that you're allowed to deploy on as a data science team. This is a good way to restrict those instances so that Inference Recommender is just searching within those instance types rather than going directly to a 24x large or a very large instance. And next, we provide your container URL, your framework version, model name, and here's the data input configuration needed for model optimization. And once all of this is into model registry, you can then kick off your Inference Recommender default job, which provides you with an instance recommendation. So here I'm just providing the job name, job description, and the type is default, which, and then here I'm providing in the input config the model package version ARN from my model registry. And this step takes around 45 minutes, 30 to 45 minutes. And what happens is, behind the scenes, Inference Recommender selects the best instance type for your ML model and payload. It runs load tests against each of those instance types and aggregates all those results together. So I'll skip down to the results just to show you how it looks. I just formatted it in pandas, but you can see there you provide your endpoint name, the instance types that are tested. Here you can see it's a C5X large, M5X large, M5 large, and a C5D large. It also provides you with environment parameters. So these variables are specific to your container. Since we're using an AWS deep learning container, Inference Recommender knows we're using TensorFlow serving under the hood, and it provides parameters that optimize the TensorFlow serving model server. And the key metrics to really look at here are your cost per hour and your max invocations, which is a measure of throughput, and your model latency, which is measured in microseconds. It's your latency from the viewpoint of your model, and not from just your model, and not including the SageMaker service. And finally, I want to also point out cost per inference. This is a useful metric which combines both your cost per hour and your throughput to see how much would it cost for every single inference if you're running your model 24/7 on this instance type. And for those of you that are new to some of these metrics, they're really just CloudWatch metrics. They're standard metrics used by SageMaker, and maximum invocations is your maximum number of invoke endpoint requests for a model endpoint. And your model latency is the time it takes for your model to respond as viewed from SageMaker. So not the end-to-end latency, but just the model. And this is measured in microseconds. So that's basically the getting started initial instance types you can get from SageMaker. It doesn't require a lot of inputs, and it's pretty quick to kick off either from Jupyter Notebooks or from Studio. I also want to take you quickly through the custom load test feature. So with Inference Recommender, let's say you already are used to using Locust or JMeter or the various other load testing tools out there. You can have the same level of customizability with Inference Recommender for your load tests, and be able to gather all your metrics from CloudWatch, as well as look at the key metrics gathered within Inference Recommender for your load tests. So here it's a little more detailed, but we're actually sweeping through container variable parameters in this load test. OMP num threads is a parameter that's specific to TensorFlow serving, and we're looking at a couple different powers of 2 and then another value to see which container parameter value gives us the best throughput and latency for this instance type. For the stopping conditions, we provide the P95 model latency, 100 milliseconds, and the throughput requirement here is 300 for invocations. We can also define a traffic pattern. So the traffic pattern, it takes as input. It can take as input any number of phases. But as an initial test, we're just starting with the traffic pattern where it's one user, one virtual user, or one thread. And we have a spawn rate of 1, which means every second we're spawning up a new user. And the whole traffic pattern duration is 120 seconds. So it's a pretty short load test. We've set a maximum job duration, max number of tests, and max parallel tests. These are really useful parameters to help you control the cost of your load test. Once you start looking at more than 10 instance types or different instance configurations, you may want to control the cost of your load test using these parameters. Now that we're at the create inference recommendations job step, we can then input our job name, description. The job type is advanced here. This role is from earlier setup. It's just a SageMaker execution role. And as input, we provide the model package, version ARN, the job duration, your instance type, and environment parameters that you're testing. And the nice feature here is you can provide a range. So instead of replicating each instance, the same instance type, you can provide a comma-separated list of values that you want to test. And then we define our limits here, our traffic pattern, and then our stopping conditions, which is our max invocations, as well as the P95 model latency. Once all of these inputs are in, we can then, it's the same exact API for submitting the job, getting the status, and then finally looking at describing the inference recommender results. And again, I formatted using pandas, so you can see the different environment parameter variables that were inputted, 2, 4, and 10. And it's actually interesting that this is an M5 X large instance, so it's 4 vCPUs, but the number of threads that works best is 2 here. So it's helpful if you want to vary different parameters in your container and figure out what's optimal in terms of throughput or latency for your use case. And we have all of this in the notebook in GitHub, but also want to quickly show you that it's easy to take the endpoint name, the region that you're in, and pull in very detailed plots from CloudWatch. So here you can see much more detail on other performance metrics such as CPU utilization, GPU utilization, your disk utilization. You can also look at if there's any 500 errors or 400 errors. And yeah, it gives you a much, using CloudWatch, of course, gives you a lot more flexibility. If there's other container metrics that you're emitting from your container, you can include that as part of your load test results. So that's pretty much a quick run through of the demo. I'll get back to the presentation and then we can take some questions. So Inference Recommender is generally available now in all commercial regions that SageMaker is available except for KIX. You could use Inference Recommender as you saw through SageMaker Studio or the AWS Python SDK or CLI. And lastly, there's no extra cost for using Inference Recommender. So the testing suite hosted by Inference Recommender is free of charge, and you only pay for endpoint instance usage during the time of the load test. And all your endpoints are cleaned up automatically. So just the period of time your load test is running that you can expect to have charges. So I hope you enjoyed the session today. I'm really excited to see all the different use cases with Inference Recommender. And thank you. Let me know if you have any questions, and yeah, please fill out the session survey. Oh, sure. In the back. Are you asking does Inference Recommender do auto scaling underneath? Okay, yeah. So it provides you with the initial instance count, which you can then use as an input into your, when you set up attach an auto scaling policy to your endpoint on SageMaker, you can input that as the initial instance count and use it alongside a request-based auto-scaling policy. Yeah. We do have it in the roadmap to monitor your endpoints long-term and come up with custom auto-scaling. Yeah. So it's whatever can support the max invocations and latency requirements that you provided. And then if it goes beyond that, you'd want an auto-scaling policy to handle it. Oh, okay. Oh, yeah. Mm-hmm. Yeah, so simple answers, we don't support multi-model right now. We're only doing real-time inference endpoints. Oh, go ahead. I wouldn't recommend, so you were asking, does this support serverless inference? And right now, we don't support serverless, and it's not something I'd recommend using for serverless just yet, but it could be something, if you're doing batch or async inference, it could still be useful. Yeah. So you're asking why do we upload the model to S3? And you're correct. If you use SageMaker for training, your artifacts are already in S3, and it's easy to, you can reference that same URL. That's right. So you're asking how will this integrate with CI/CD pipelines? There's a little bit of configuration to do, but the advantage is model registry is already integrated with CI/CD. So once your models are in model registry, you can use SageMaker pipelines to automate the CI/CD part and add an extra step for inference recommender to figure out the right instance type after the changes are in. Oh, sure. Yes. So it'll work with custom containers. The only thing we can't quite support yet is the model level optimizations and container parameters, since we don't know what underlying model server and you have in your custom container. Mm-hmm. So you're asking if you extend a AWS deep learning container, and would inference recommender be able to support that? So the short answer is it supports all containers, but we could talk offline. I could see it's a little tricky because we don't know if we rename your container. If you rename the container tags, it's hard to know how to match it with the original. But yeah, we could definitely offline about that. Any other questions? Oh, yeah. It's not specific to batch transform, but with batch transform, you might want to maximize throughput, or you can still use the recommendations for the ML model. You can know at least the performance characteristics, but we are looking to extend it, so there's an experience specific to batch transform. Oh, sorry. Not at the moment. It's available through the Botto 3 Python SDK, but I'd love to hear your inputs later on how you'd like to integrate in the Python SageMaker SDK. Any other questions? Oh, that was good. Great. I'm happy to chat outside. I'll be around. Thank you.